All right, so today we're going to tackle climate change, but maybe from a slightly different angle. We're going to zoom way out to understand the fundamental forces that have shaped our planet for billions of years. Because, to really get a handle on what's happening now, you've got to understand the deep past.
This quote really nails it. The idea that Earth has ever had a perfectly stable, unchanging climate, it's just not the reality. Change isn't some weird exception, it's the rule, it's the baseline. No 2 years are ever exactly the same, let alone 2 centuries.
And we can see this change happening right before our eyes, even within a single lifetime. Just look at this. This is the Grinnell Glacier up in Montana. These pictures, taken over just a few decades, show it literally disappearing. You don't need a science degree to see what's happening here. It's just a powerful visual reminder that our climate is a dynamic, moving thing.
Okay, so that brings us to the big question for today. If change is the one constant, then what's pulling the levers? What are the massive forces that have always warmed our planet up and cooled it back down? Well, to answer that, we first have to pop the hood and understand the machine itself.
See, before we can even talk about climate change, we have to get a handle on the climate system. And it's way more than just the air around us. It's this incredibly complex, deeply interconnected network.
So here's the crucial part. None of these pieces work alone. The oceans, the ice caps, the land, every single plant, and the atmosphere, they're all tangled up in one massive, integrated system. You make a change in one part, and you're going to get ripples spreading through all the others.
Take a forest like this one, for example. It's not just sitting there looking pretty. It's actively shaping the climate. It reflects solar energy, and it acts like a giant plumbing system, pulling water from the ground and pumping it into the atmosphere. That process alone has a huge impact on humidity and even whether clouds can form.
Then you've got what scientists call the cryosphere, all the ice on our planet. These massive ice sheets and glaciers are like the Earth's giant mirrors. They reflect sunlight back out to space, which helps keep things cool. So naturally, as they grow or shrink, they change that reflectivity. And, of course, they have a massive impact on sea level.
And finally, the land itself. Deserts, mountains, plains, they all play a role in how energy gets absorbed or bounced away. The location and even the height of a mountain range can completely change wind patterns and dictate the climate for an entire continent. It really is all connected.
So now that we have a feel for the system, let's look at the enormous natural forces that act on that system. These are the planet's natural pacemakers, the things that have set the rhythm for climate change throughout Earth's long history.
When you boil it all down, scientists have identified 4 main natural drivers. These are the heavy hitters: the slow dance of the continents, wobbles in Earth's orbit, huge volcanic eruptions, and even changes in the sun's own energy output.
Tectonic activity is the slowest of the bunch, but wow, is it powerful. We're talking about continents drifting over millions of years. This map shows you what the world looked like 94 million years ago. As oceans opened up and closed off, it completely rewired the planet's circulatory system of ocean currents and winds, fundamentally changing the global climate.
Then you've got these things called Milankovitch cycles. Sounds complicated, but they're just predictable, long-term changes in Earth's orbit around the sun. Things like the shape of its orbit, the tilt of its axis, and this little wobble. These cycles change how sunlight gets spread out across the planet, and they are basically the master clock for the coming and going of ice ages.
Now, on shorter timescales, you have other forces at play. A massive volcanic eruption, like Mount Pinatubo here, can blast so much stuff into the high atmosphere that it actually reflects sunlight and can cool the entire globe for a year or two. And our sun isn't perfectly constant either. It has its own cycles that cause small little shifts in the energy we receive.
Okay, so this is all pretty fascinating, but it probably has you wondering something pretty obvious. How on earth do we know any of this? How can we possibly know what the climate was like when dinosaurs were walking around? Well, it's an absolutely incredible story of scientific detective work.
Seriously, think about it. We've only had reliable thermometers and weather stations for maybe 150 years. So how do you reconstruct the climate of the deep past? Well, it turns out the Earth keeps its own records.
Scientists have gotten incredibly clever at reading the clues left behind in these natural archives. Ancient ice cores have tiny bubbles of prehistoric air trapped inside. The width of a tree's rings tells a story of wet years and dry years. Even the chemistry of ancient coral skeletons and fossils can tell you the temperature of the oceans they lived in.
This is the key idea right here: proxy evidence.
These aren't direct thermometer readings from the past, of course, but they're really reliable stand-ins that let scientists reconstruct past climates with amazing detail. And by cross-referencing lots of different proxies, they can build a really robust picture of Earth's history.
Okay, so we've looked at the Earth system, and we've looked at the giant forces that act on it. But there is one more critical piece to this puzzle we need to understand, and it all has to do with our atmosphere, the greenhouse effect.
The process itself is actually pretty simple, and honestly, it's absolutely essential for life as we know it. Energy from the sun comes in through the atmosphere and warms up the planet's surface. Then, the Earth radiates some of that energy back out as heat.
And this is where greenhouse gases come into play. Certain gases, like carbon dioxide, methane, and even water vapor, are really good at absorbing that heat that's trying to escape. They trap some of it, acting like a natural blanket that keeps our planet at a livable temperature. Without this natural greenhouse effect, Earth would just be a frozen ball of ice.
So, the crucial point is that these gases have always been part of the system. They come from natural sources like volcanoes and wetlands, and they get absorbed by natural sinks like oceans and forests. But, starting with the Industrial Revolution, human activities, mostly burning fossil fuels and deforestation, started adding these gases to the atmosphere much, much faster than natural systems can remove them. We've essentially been making that planetary blanket thicker.
And this has very real, very tangible consequences. Just look at the difference in the minimum amount of Arctic sea ice between 1980 and 2020. That's a stark difference. It's just one of many indicators that show these rapid changes in our atmosphere are having a measurable impact on that big Earth system we talked about earlier.
So when you step back, you see our planet's climate is this epic story of constant change, driven by massive natural forces over incredible spans of time. The system has always been in flux, but now, for the first time in this entire planetary story, one single species has become a geological force in its own right. And that leaves us with a pretty profound question, doesn't it? What will the next chapter be?